Hello, myself Vishal Sandeep Thakur, a graduate student of Memorial University, is going to present a topic heat energy storage with the help of thermochemical materials with the help of my friends Harsh Amrish Kumar Nakub and Shivam Parmar under the guidance of Dr. Mohsin Jamil and supervision of Dr. Mahabori. Talking about thermal energy storage, it is a system that can store heat or cold to be used later at different conditions such as temperature, place or power. Here in figure 1 shows a basic representation of heat energy storage system. Here storage, chiller, building load, expansion device and pumps are shown, and the excess energy, or we can say the surplus energy, is stored in the storage. Thermal energy storage is a system which stores surplus energy or heat. It is further divided into three parts, that is sensible heat storage, latent heat storage and chemical energy storage. In sensible heat storage, the heat is stored in the form of solids and liquids. In latent heat storage, it is stored in the form of solid liquid, liquid gaseous or solid solid. And the main focus of our topic is chemical energy storage, in which chemical reactions take place to store surplus energy. Before moving ahead towards our topic, we need to first compare the three heat storage systems. Talking about the principle, sensible heat storage is stored as sensible heat in storage material by increasing its internal energy, that is change of temperature of storage media. Whereas in latent heat storage, thermal energy is stored by phase change of material at constant or near constant temperature as heat of fusion. In TCES or thermochemical energy storage, it relies on energy absorbed, that is endothermic, and released, that is exothermic, in breaking and reforming molecular bonds, respectively in completely reversible chemical reactions. Talking about the materials, pebbled bed, bricks, sand, cast steel, cast iron, etc. are used in sensible heat storage, whereas in latent heat storage, organic and inorganic such as salt hydrates, metals, etc. are used. In thermochemical energy storage, carbonates, hydroxides, metal hydrides, metal oxides are used. Now the point to be noted here is of volumetric energy storage density of TCES, which is very high at around 500 kilowatt hour per meter cube compared to the two sensible heat storage and latent heat storage. Also, the gravimetric energy storage density is nearly 1 kilowatt hour per kg of TCES. Storage period, when calculated, was found to be theoretically unlimited in TCES, and also we can transport relatively long distance in TCES compared to the other two. As shown in figure 3, high temperature thermochemical energy storage is classified into solid gas reaction and gas-gas reaction. In solid gas reactions, carbonates, hydroxides, metal hydrides and metal oxides are there, whereas in gas-gas reaction, ammonia synthesis dissociation, methane reforming and sulfur-based thermochemical energy storage are there. Here, our main focus will going to be on solid gas reactions, where we will be mainly focusing on cobalt oxide, which is a pure metal oxide, and calcium hydroxide. Thermochemical energy storage can be mainly used to recover heat from the industries, thermal energy transportation, solid oxide fuel cells, and also in solar thermal power plant. Thermochemical reactions are reversible in nature, with the thermal energy being supplied and released during the endothermic and exothermic steps respectively. Here in the operation of TCES involves three significant steps. Those are charging, storage and discharging. As shown in figure 5, when an energy is given to a reactant AB in the form of heat, the excess heat is stored in the form of products such as A and B. Now, as per the application, when we want to reuse that excess energy or heat, we can simply supply heat and discharge it in the form of reactant. Calcium hydroxide, traditionally called slaked lime, is an inorganic compound with the chemical formula CaOH2. It is colorless crystal or white powder and is produced when quicklime is mixed or slaked with water. Calcium hydroxide is produced commercially by treating lime with water as shown in the reaction below. Here in figure 6, structural representation of calcium hydroxide is shown. Now the question is why we selected calcium hydroxide instead of other materials. So calcium hydroxide offers various advantages such as it is cheap industrial mass product and abundantly available worldwide. Secondly, the reaction enthalpy is high, leading to high possible energy storage densities. Also, the charging and discharging temperature of the reaction can theoretically be adapted in a wide range of approximately 300 to 650 degrees Celsius. The applications of system could potentially be beneficial for many high-temperature processes such as storage and utilization of industrial waste heat or as an alternative storage solution in future concentrated solar power plants. Now, the working principle of calcium hydroxide is shown in which the formation of calcium hydroxide is there. Calcium hydroxide is heated during dehydration and breaks down into calcium oxide and water vapor. This type of reaction is called endothermic reaction and the process is called charging process. Now when a reaction is exothermic, heat is produced when water is heated to steam, which then interacts with calcium oxide to make calcium hydroxide and release heat. This type of reaction is called exothermic reaction and the process is called discharging. Since the thermal storage performance is closely concerned with specific heat capacity, energy density, and reaction enthalpy, so in this slide, the specific heat capacity of calcium hydroxide is shown in table 2. As the researchers performed various specific heats based on their temperature range. As we can see, when the temperature of calcium hydroxide was 273 Kelvin, its specific heat was 1141 joule per kg Kelvin, and it is increased as the temperature increased. As shown in figure 8, a line graph of temperature versus heat capacity of calcium oxide and calcium hydroxide is shown, where the temperature range between 25 degrees Celsius to 500 degrees Celsius. As we can see, heat capacity was slightly increased as the temperature increased from 10 degrees Celsius to 500 degrees Celsius. Now the reaction enthalpy can be calculated from Van 't Hoff's equation, that is logarithm of pressure is equal to reciprocal of change in enthalpy upon RT, that is gas constant and temperature plus constant. Van 't Hoff's equation has been widely utilized to explore the changes in state function in a thermodynamic system. The Van 't Hoff's plot, which is derived from this equation, is especially effective in estimating the change in enthalpy and entropy of a chemical reaction. Researchers plotted the relationship between logarithm of P, that is pressure in bars, and the reciprocal of the absolute temperature T in degrees Celsius, which is shown in figure 3 of calcium oxide and calcium hydroxide. After calculating the slope, it was found to be 104.18 kJ per mole of reaction enthalpy when the temperature range was around 300 to 510 degrees Celsius. To sum up the topic of calcium oxide and calcium hydroxide, we also need to discuss the existing drawbacks and solutions of calcium hydroxide. After researching, we came to know that drawbacks such as high decomposition temperature, low thermal conductivity, formation of agglomeration, and problem of carbon dioxide was seen, where the proper solutions were given, out of which for high decomposition temperature iron doping was suggested, for low thermal conductivity reactor design and adding composites were suggested, for formation of agglomeration compositors were suggested, and for carbon dioxide usage of filter were recommended.
Now moving further ahead, the next one is the thermochemical heat energy storage with the help of cobalt oxide CO3O4. The schematic diagram represents the structure of cobalt oxide. Cobalt oxide is a black antiferromagnetic solid material. It adopts the normal spinel structure with CO2 plus ion in tetrahedral interstices and CO3 plus ion in the octahedral interstices of the cubic closed packed lattice of oxide anions. Moreover, cobalt oxide generally consist of cobalt and oxygen atoms, and the compounds in the cobalt oxide family includes cobaltous oxide COO, cobaltic oxide CO2O3, and cobalt oxide CO3O4. The main reason we chose cobalt oxide as thermochemical heat energy storage material because cobalt oxide is the most promising redox material among pure oxides for thermochemical energy storage application due to its high reaction enthalpy and also have relatively moderate conversion temperature. Also, it has a high energy storage density, has good cyclic stability, has no catalyst required. it also possesses complete and reversible reaction and also has a fast kinetic reaction. However, when it comes to disadvantages, it has a high material cost, it's toxic in nature and has a problem of shintering. Now moving further ahead, the next slide is about the working principle of cobalt oxide. So the cobalt oxide stores energy in two forms. The first one is energy storing and the next one is energy releasing. The schematic diagram represents the redox reaction in the thermochemical energy storage system. As we can see in this diagram that the input energy comes from the boiler or from any sources like sun strikes into the cobalt oxide material. After that, the cobaltous oxide and oxygen got separated and energy is stored. This phenomena of capturing energy with the help of cobalt oxide is called energy storing. Later, when we need to use this stored energy, release it and it gives the energy. This process is called energy releasing and we can use this energy whenever we need it in future applications. Now moving further ahead, the next slide is about the experimental effect of specific heat. Specific heat of the storage material is an essential parameter for the storage system's thermal capacity when the storage material mass is constant. The first graph shows the temperature versus time graph, where the effect of specific heat of the solid material on the outlet temperature is shown. In all three graphs, specific heat was 900, 1200 and 1500 joule per kg Kelvin. In the first graph, air outlet temperature increased to 1350 Kelvin in just 4 hours when specific heat was 900 joule per kg Kelvin and reached up to 1280 Kelvin with 1500 joule per kg Kelvin specific heat within the same period. With smaller specific heat, the outlet air temperature dropped quickly during discharging, while higher specific heat resulted in more gradual heat release. The second line graph shows the total mass versus time graph. The reduction period was 45 minutes shorter when specific heat was 900 joule per kg Kelvin compared to 1500 joule per kg Kelvin. In the last graph, the mass of conversion rate of cobalt oxide inside the whole storage system is shown. That is the whole reaction rate based on mass of CO3O4. The negative value represents the reduction period and the positive value indicates the oxidation process. Moving further ahead, the next slide is about the effect of heat transfer coefficient. Another consideration about the heat storage system is the volume. It is better to have higher heat transfer coefficient to make the storage volume smaller. Figure 1 demonstrates the outlet air temperature with a different heat transfer coefficient and conversion rate of cobalt oxide. Both the figures have specific heat 900, 1200 and 1500 joule per kg Kelvin. The first graph shows the influence of different wall thickness of the channels on air outlet temperature. When inner diameter of channel is fixed, during charging process, air outlet temperature changes more gradually and reaches to lower peak value for larger wall thickness. Air temperature reach up to 1350 Kelvin within 4 hours for 0.001 meter thickness wall and up to 1300 Kelvin for 0.004 meter thickness wall. The second graph shows the mass conversion rate of cobalt oxide in charging and discharging process. The reaction rate of the whole storage system based on mass of cobalt oxide. More quickly the temperature increases and or decreases, shorter the reduction or oxidation process are.
It is very crucial to discuss about the reactors used in solid gas reactions. As shown in figure 17, classification of solid gas reactors are shown. Solid gas reactors are classified in three parts, that is fixed bed reactors, fluidized bed reactors and moving bed reactors. In fixed bed reactors, direct contact type and indirect contact type reactors comes. In fluidized bed reactors, endothermic and exothermic type of reactors comes. And in moving bed reactors, shell and tube type, rotary kiln type and screw extruder type reactors comes.
The reactors in this research on calcium oxide thermal storage systems are small scale because it is currently in laboratory development stage. The researchers studied the heat storage efficiency in different reactors, so it is crucial to choose the right reactor. Fixed bed reactors. Fixed bed reactors are widely used due to their simplicity of operations. Because of the limited thermal conductivity of indirect reactors, direct heat transfer reactors are the best alternative. Researchers claim that the reaction rate is the most influential parameter for the reactor's efficiency. The experimental findings show that the greater the charging temperature during the charging stage, the faster the heat storage rate will be. A new indirect reactor was designed, and experimental demonstration of hydration dehydration under low vapor pressure was explored. The results suggest that it is possible to run the storage system at low vapor pressure. In moving bed reactor, the moving bed is believed to reduce the pressure drop and heat and mass transfer obstacles in a fixed bed. Diagram of fixed bed reactor is shown in figure 19a. This reactor adopts a counter-current form. Unreached contact material enter the pipeline from the top and hot air enters the reactor from the bottom. Heat is transferred by a hot fluid that flows on one side of the heat exchanger cell and is guided by a baffle. These plates ensure rapid air circulation. Fluidized bed reactor. Researchers designed a fluid bed reactor and developed a model to predict the reaction process to solve the limitation of a fixed bed heat and mass transfer. The results demonstrate that the response rate has increased considerably. The researcher performed hydration and dehydration tests in a 5.5 kWh fluidized bed reactor and developed a model to validate the results. Figure 19b depicts the experimental apparatus. However, due to the significant temperature difference between top and bottom of a large fluidized bed reactor, calcium oxide calcium hydroxide reaction is insufficient. The restriction has not yet been addressed. As a result, more remarkable efforts will be required in the future to develop and run large-scale reactors in industrial uses. Our next topic is cobalt oxide reactors. A directly irradiated moving particle reactor and fixed bed reactors were studied. The moving particle reactor has a number of benefits, including a large surface area and the ability to move materials. However, it is fundamentally difficult to move reactors parts at high temperatures. The fixed bed reactors are simple in construction, but they have limitations in obtaining a good HTF distribution along the bed, sintering of the reactive material and higher pressure drop. According to several researchers, a mentioned problem can be solved by utilizing foam-shaped monoliths or structured honeycomb shape for the HTF to flow through. These honeycombs with structures offer more surface area and effective heat transfer. The proposed arrangement has already undergone a lab-scale proof of concept validation that included semi-quantitative heat effects calculation and their association with redox processes and structural impacts during operation. An air-operated solar thermal power plant that can be combined with thermochemical storage is depicted conceptually in figure 21. In figure 21a, storage module and a power block are connected in series, and in figure 21b, storage module and a power block are connected in parallel. It gets ideally heated in a solar receiver and flows through the storage reactor during charging operation. It transmits heat to the solid material, which subsequently undergoes an endothermic chemical reaction after first heating up. From the outlet of the power block, cold air is fed to the storage medium during discharging or off-sun operation. After taking chemical sensible energy from the reactive material, the cold air from the power block is heated. During the hours when it is not sunny, this heated air can be sent to the power block to generate electricity. In the series configuration, heated air from the receiver is utilized to charge the reactor during the charging process before being delivered to the power block.